Imagine this. You pull a bottle of water out of the freezer, and instead of ice, it's still liquid. But the moment you tap the bottle on the table, whoosh, it instantly freezes before your eyes. It looks like magic, right? But it's not magic at all. It's a mind-bending phenomenon called supercooling. And today, we're diving deep into the strange physics behind it. Water is supposed to freeze at 0 degrees Celsius, but supercooling breaks that rule. It's water slipping past the laws of nature, or at least that's how it feels. In reality, there's an elegant science behind why water can stay liquid even at 5, 10, or sometimes even colder. And here's the wild part. In some situations, no matter how hard you smack it, supercooled water still won't freeze. Now you might be thinking, okay, cool party trick, but why should I care? Well, scientists actually care a lot. In cryogenics, the science of freezing and preserving living tissue, ice crystals are the enemy. They're sharp, they puncture delicate cell walls, and they destroy life at the microscopic level. But if you can stop those crystals from forming, you can give frozen cells a fighting chance at survival. Suddenly, supercooling isn't just fun, it's the key to preserving life, maybe even the dream of freezing astronauts for long space journeys. So what's really going on inside a bottle of water when it's supercooled? Think of it as a battle between two forces. Inside the ice crystal, molecules want to freeze. That's the low-energy, stable state. But on the surface of the crystal, things get messy. Surfaces require more energy, and in this case, the surface would rather stay liquid. Here's the kicker. The size of the crystal decides who wins. Tiny crystals. They have way more surface compared to their interior, so the stay liquid side always wins, and they melt back down. Bigger crystals, their interior dominates, and once they cross a certain threshold, the critical size, they keep growing, freezing everything in sight. At 4 degrees C, that threshold crystal is about 20 nanometers wide, roughly 70 water molecules across. At 10 degrees C, it only needs to be 10 nanometers. That's why colder water freezes faster. It's easier for a crystal to hit the critical size. This is why pure water in a supercooled state can just sit there, looking totally calm, until something gives it a nudge, like dust, minerals, or even your hand smacking the bottle. Suddenly, boom, ice takes over in a flash. But the story gets even stranger. When water freezes, it expands. If it's trapped in a rigid container, that expansion creates pressure, and pressure fights against freezing. In fact, if the container is tiny enough, smaller than a few hundred nanometers, pressure wins every single time. No matter how cold the water is, no matter how much you shake it, it simply refuses to freeze. Imagine water trapped in a nano-sized bottle, forever liquid below zero. It sounds like science fiction, but it's real physics. Of course, there's a loophole. If you want that supercooled water to finally freeze, just open the container. Release the pressure, and suddenly the laws of physics shift back. Give it a little nudge, and the entire thing snaps into ice in an instant. So the next time you see a bottle of water transform into ice before your eyes, remember, it's not magic. It's a delicate dance of physics, surface tension, volume, and pressure all battling it out inside a single drop. From futuristic cryogenics to everyday kitchen experiments, supercooling shows us that even something as ordinary as water still has secrets waiting to be discovered. Because sometimes, the simplest things hide the most extraordinary science.